we will be learning about electric dipole. By definition, a dipole consists of a positive charge and a negative charge separated by a finite distance. Consider a dipole with a positive charge plus q placed at A and negative charge minus q placed at B at a distance of 2a. Thus, distance between the charges is referred to as the length of the dipole. For an electric dipole, the midpoint O of the line joining the dipole is called the center of the dipole, and the straight line passing through the charges and also through the center is called the axis of the dipole. Assume that the dipole is placed such that the center O of the dipole coincides with the origin, and the axis of the dipole coincides with the x-axis of the Cartesian coordinate system. The charge minus q is placed along the positive x-axis, and the charge plus q is placed along the negative x-axis. The product of the length of the dipole and the magnitude of the charge is called the electric dipole movement P. Here, P is equal to 2aq, which is a vector quantity directed from minus q to plus q. Let us now obtain the electric field strength E at point T on the axis of the electric dipole, which is at a distance x from the midpoint O of the dipole. The magnitude of electric field strength E due to a charge q at a distance r from it is given by E is equal to 1 by 4 pi epsilon naught into q by r square. The magnitude of the electric field strength E1 due to the charge plus q is equal to 1 by 4 pi epsilon naught q by x plus a square. Let us label it as equation 1. The direction of this electric field is in the direction opposite to that of dipole moment. The magnitude of the electric field strength E2 due to the charge minus q is equal to 1 by 4 pi epsilon naught q by x minus a square. Let us label it as equation 2. The direction of this electric field is in the direction of the dipole moment. Point D is nearer to the charge minus q than the charge plus q. As the distance of the point P from minus q is lesser than that from plus q, the magnitude of the electric field strength E2 is greater than E1. Hence, the magnitude of the resultant electric field strength E at the point D is equal to E2 minus E1. Let us label this as equation 3. The direction of the resultant field strength at the point is in direction of E2. Substituting the value of E2 and E1 and simplifying, we get the expression for the electric field strength E as 1 by 4 pi epsilon naught or qx by x square minus a square whole square. Let us label it as equation 4. On further solving the equation 4, we get E is equal to 1 by 4 pi epsilon naught 2x into 2aq by x square minus a square whole square. Please note that in this equation, 2aq is the magnitude of the dipole moment P. Therefore, E is equal to 1 by 4 pi epsilon naught 2px by x square minus a square whole square. Let us label this as equation 5. When the point T is at a very large distance from center O, then x is very large compared to point A. Then, writing the expression 5 as an equation 6 and neglecting the term a square by x square for x, which is very large as compared to a in equation 6, and on further simplification, we get E is equal to 1 by 4 pi epsilon naught 2px by x power 4. Let us label it as equation 7. This can be further simplified as E is equal to 1 by 4 pi epsilon naught 2p by x cube. Let us label it as equation 8. Equation 8 can be expressed as 1 by 4 pi epsilon naught 2p by x cube into p cap, where p cap is the unit vector along the dipole axis in the direction of minus q to plus q. Let us label it as equation 9. Let us now obtain an expression for the electric field strength E at point F on the axis on the equatorial plane of electric dipole. Let point F be at a distance y from the center of the dipole. The point F is at a distance r and is equal to root y square plus a square from each charge of the electric dipole. Let us label it as equation 10. At the point F, the positive charge creates an electric field of magnitude. E1 is equal to 1 by 4 pi epsilon naught q by r square. Let us label it as equation 11. Electric field strength E1 is directed away from the positive charge and acts along the line joining the charge plus q and point F as shown. Similarly, the negative charge creates an electric field of magnitude. E2 is equal to 1 by 4 pi epsilon naught q by r square. Let us label it as equation 12. Electric field strength E2 is directed towards the negative charge and acts along the line joining the point F and the charge minus q as shown. We observe that the magnitude of E1 is equal to that of E2. The point F lies on the perpendicular bisector of the line joining the charges plus q and minus q. Hence, by geometry of the triangle FAB, the angle FAO is equal to the angle FBO. Let this angle be theta. Now, the angle E1FE2 is the exterior angle of the triangle FAB and hence is equal to 2 theta. The resultant of E1 and E2 is obtained by using the parallelogram rule for vector addition. According to the rule, the resultant of E1 and E2 is obtained by diagonal of the parallelogram formed by the vectors E1 and E2 as the sides. Since the magnitudes of E1 and E2 are equal, the lengths of the vectors representing E1 and E2 are also equal. Hence, the diagonal of the parallelogram formed by the vectors E1 and E2 as sides bisects the angle 2 theta. Thus, the resultant of E1 and E2 makes an angle theta with the direction of both E1 and E2. The resultant of E1 and E2 is parallel to the x-axis and is directed along AB. Let us consider the components of E1 and E2 along the x and y axes to find the magnitude of the resultant electric field at the point F. The components of the electric field E1 along the x and y axes are E1x and E1y respectively as shown. And the components of the electric field E2 along the x and y axes are E2x and E2y respectively as shown. Since the electric field strengths E1 and E2 are of equal magnitude, the components E1x and E2x will be equal. Similarly, E1y and E2y will be equal. We also observe that the components E1y and E2y are oppositely directed and so cancel each other. Therefore, at the point F, the resultant electric field strength E is equal to E1x plus E2x. Let us label it as equation 13. As the angle between E1 and x-axis is theta, the component E1x is equal to E1 cos theta. Substituting the magnitude of E1, we get E1x is equal to 1 by 4 pi epsilon naught into q cos theta by r square. Let us label it as equation 14. Similarly, the angle between E2 and x-axis is theta, and hence the component E2x is equal to E2 cos theta. Substituting the magnitude of E2, we get E2x is equal to 1 by 4 pi epsilon naught into q cos theta by r square. Let us label it as equation 15. Substituting equations 14 and 15 in equation 13 and simplifying, we get the magnitude of the electric field at point F. E is equal to 1 by 4 pi epsilon naught into 2q cos theta by y square plus a square. Let us label it as equation 16. From trigonometry of either of the triangles FAO or FBO, we get cos theta is equal to a by r. Substituting the value of r, we get cos theta is equal to a by square root of y square plus a square. Let us label it as equation 17. Substituting equation 17 in equation 16 and simplifying, we get the equation for the magnitude of the resultant electric field E at point F. Since the dipole moment T is equal to 2aq, we get E is equal to 1 by 4 pi epsilon naught into p by y square plus whole power 3 by 2. Let us label it as equation 18. The direction of the electric field strength at the point F is opposite to that of the electric dipole moment and parallel to the axis of the dipole, as discussed earlier. When the point F is at a very large distance from the center O, then y is very large as compared to A. Then, writing the expression 18 as in equation 19 and neglecting the term a square by y square for y, which is very large as compared to A in equation 19, and on further simplification, we get E is equal to 1 by 4 pi epsilon naught p by y cube. Let us label it as equation 20. In vector notation, electric field strength E can be expressed as shown in equation 21. The negative sign is used since the electric field strength E is opposite to the direction of the unit vector p cap. For a given dipole, the magnitude of the dipole moment P is constant. From the expression of the dipole moment, we get charge Q is equal to P by 2A. Hence, as the length of dipole 2A tends to 0, the magnitude of the charge Q tends to infinity, so that the dipole moment P is equal to 2AQ becomes finite.